So we have a Y-connected generator, and we also have a delta-connected generator, symbolized by the Greek letter delta, which looks like our standard isosceles triangle. So we have the current from A to C, or from C to A, whichever way the current's flowing. It's flowing both ways each half cycle, because it's alternating current. It goes one way and then switches around, and goes the other way, and then repeats. So we also have the voltage across each here, voltage C to A to B, B to C. So there is a definite cycle around which a magnet inside these coils would rotate. If it rotates, say, counterclockwise, then it starts with A to B, and it would go B to C, and then it goes C to A. This would be a clockwise rotation. That's your phase condition. So phase sequencing, the sequence of A to B coil, then B to C coil, then C to A coil, phase matters in both delta and Y configuration. So it determines the direction which your generator is spinning. So again, you're going to have the same voltage, but on your load, but then your current, the current is, well, Isabel here is line voltage here, so L is load, in some cases it's line, in others it's inductor, in others. So again, when you see a letter reused in electrical engineering, which after a while you'll notice kind of a lot, just look at the context of how it's being used. So we're in transformers, we're looking at a generator, so the L here must be the line voltage, which is the same as the phase voltage here. Then the current draw is going to be square root of 3 times any one leg of the generator. This is a leg, that's a leg, that's a leg. Each coil of wire, each inductor. So the current from big A to little a is going to be square root of 3 times the current from B to A, which is our line current, at the angle negative 30, 150, and 90. We have our currents, we have our voltages. Our voltages are, of course, 120 degrees apart, negative or positive. That's still true just as it was for a Y generator. Now, it's also possible to have a Y and a delta generator connected up together. So here we have our Y generator with our 3 legs, A to neutral, B to neutral, C to neutral. And the neutral line would not connect anywhere in a delta generator because there's nowhere for it to connect to. So in this case here we have our line current, we have our, say, from B to A is our Y line voltage, and then here we have our impedances in our voltages. They can be resistors, capacitors, inductors, any load. Again, this only covers balanced loads when all impedances are equal. So we follow Kirchoff's current law. Currents entering and leaving a node are going to add up to 0. So that means our current is on our line is going to be the square root of 3 times the current in the phase. So here we have the phase, we have 2 legs of the generator using one impedance. Let's say if we just go from point A to point B and go around, well, there's just one. So we have the current from here and the current from here and just one impedance using it. So we multiply. You're always going to multiply or divide by the square root of 3 to get your other value, or it's going to be the same. It's as for y, it was the same as y delta. You can also do a delta y, but it's similar. You just flip this as your generator and this configuration as your load. So, balanced total power. So P sub T is our total power, is going to be, again, square root of 3 times your line to line, or just plain line voltage, times your line current, times your cosine theta. And this will give you our resistive, our power. You see here, this resistive power. Let's look at this triangle here. This is what electricians use as opposed to, say, electrical engineers. And sometimes the engineers and the electricians have to meet on a common ground. So here we have a right triangle of a real axis here. Imagine this is real numbers. For, remember our complex algebra, this is the real number plane. This is power. So power, being voltage times current, is resistive. So that goes on the horizontal axis. Then we have Q, and Q is our reactive power, or VARs, VAR, volt amp reactive. So the S at the end is just plural, more than one VAR is your VARs. And then your S is your apparent power, or what you call your volt amps. And wait, and you're probably thinking, wait, isn't volt amps just volts times amp is just power? Yeah, but it's simpler than that. It's different. It can change. Like, this also plays into transformers as well. Your volt amps, your apparent power. That's the hypotenuse of your right triangle. You can use Pythagorean's theorem to find it. P squared plus Q squared equals S squared. So the square root of P squared and Q squared. Root that, and you get S, your apparent power. And then, so getting back to that Q on your imaginary axis, well, imaginary axis, this is your J, your reductors, or capacitor, is your E and I, and sine of theta, and then your S, your apparent power, square root of 3 times just the volts and amps, without the power factor. And the power factor, F sub P, is P sub T over S sub T. So, there you go. There's three-phase balanced load total power. A little more about S, P, Q, and R. Mind your P's and Q's. Mind your P's and Q's, your P being your real power, and your Q's being your VARs, your apparent power. So, going in with these diagrams, this is for comparison's sake, as I was just mentioning. So Z is your impedance, R is your resistance, and this is XL minus XC. Remember when we were looking at RLC circuits, then finding resonant conditions in series and parallel, XL minus XC was in there. It's on their J, or imaginary axis. R is on a horizontal axis. The impedance is the square root of the sum of the squares. And here, this, in the same manner, as I just explained, is your P is real, Q is your VARs, S is the apparent. For powers, see V times I is power squared plus VAR squared. Resistive power for just resistors. So let's say if a particular impedance on each leg of a Y or a delta load was made up, say, of a resistor and a capacitor in parallel, then you would only take the resistors, you would only account for the resistors when calculating. As opposed to, say, the reactive power, you would only account for your inductors or capacitors when calculating. Now keep in mind that I say when calculating, now define your current I. So I is V over R, or for alternating current, V over Z total. So when you find your current, use every element, whether in series or parallel, in each leg of the capacitor to find its impedance. Use all of them to get your current to use here. And then your volts equals, well, I times your resistance, or I times your inductance, or I times your capacitance. So just, you want to keep those two straight. And then your power factor is your P over S, between negative 1 and 1. Well, power factor is always going to be 0. Remember, it's a cosine. Well, it's going to be between 0 and 1, actually, because cosine function always returns positive. So loads, if you have a load in series, you're going to use I squared R, because the voltage across to, if you have a load in series, you want to use power equals I squared R, because the current through two elements is the same. And what that means is that if we use the current, then we know it's the same across two elements, even if the voltage across the elements may differ. And if we have them in parallel, well, in parallel elements, the voltage across each element is the same. So we use voltage squared over R to get our power. And the total power is, well, once we solve power for each leg, delta or Y, then you just add up the three powers, or take one leg and multiply it by 3 in a balanced load, and there's your three-phase power. That's all I have for now. Thanks for watching, and tune in for our next episode.